Hey everybody, welcome to our video today, which is all about photoelectron spectroscopy. So earlier in the unit, we were talking about mass spectrometry, spectroscopy. There's kind of mean the same exact thing. But in this case, we're talking about something a little bit different. So mass spectrometry was able to tell us the percentage of isotopes that are present in a particular sample. And if you remember all the way back to the beginning of the notes, the way that that's done is it's basically using a magnet. In this case, we're using a little bit of a different procedure that can help us to determine essentially ionization energies for different elements. So before we get into that part of it, let's go ahead and just talk a little bit about the photoelectric effect, because this will help us to understand photoelectron spectroscopy. So the photoelectric effect, what is it? Well, this is the emission of electrons when electromagnetic radiation, such as light, hits a material. So we're going to be talking about this in terms of metals. So I just have this image here, and I wish I could have put this stuff up on different, like using animation, but I couldn't separate everything. So anyway, we have a metal surface, and we're going to shine some sort of white light onto this surface. So this right here contains all the colors of the visible light spectrum. So red, orange, yellow, green, blue, indigo, and violet. I didn't have indigo on there because I don't really even know what indigo is, so it's not there. But anyway, when you shine a light source on a piece of metal, there are electrons that are ejected from that surface. And when those electrons are ejected from the surface, we can measure that. We can measure the energy that those electrons have. We can measure their frequency, we can measure their wavelength, and in turn use that to help study elements. So we call those electrons that are emitted from the surface photoelectrons. So the frequency or the energy or the wavelength, because they're all connected to one another, if you remember back to Chem 1, any of those of light determines if those electrons are ejected and with what amount of energy. So of course we can measure that. And the intensity or brightness of the light that comes off of this surface tells us how many electrons. So if there's a very intense light that's coming from that, we know that there were a lot of electrons that were ejected. So how does this relate to what we're talking about with electrons? Well, let's take an example here. So it requires much less energy to remove the outermost electrons from an atom. We've talked about that already. Those electrons aren't pulled in as close to the nucleus because of Coulomb's law. The farther away electrons are from the nucleus doesn't have as strong of a pull on them. So they're easier to remove the larger the atom gets. And visible or ultraviolet light actually has enough energy to remove the outermost valence electrons for all atoms. So we can remove those valence electrons pretty easily just by shining a light onto elements, particularly visible light or ultraviolet light. So what if you want to remove all the electrons from an atom? Because we want to determine, what does an element look like? What's the structure of the element? What is going to be the electron configuration of this element? And what do we want to do if we want to remove all of the electrons from an element, not just those valence electrons? We need a much stronger source of radiation in order to do that. So in order to study photoelectron spectroscopy, we will use something different. So let's look at the successive ionization energies for the element lithium. So lithium's configuration looks like this: 1s2, 2s1, has 3 total electrons, but has 1 valence electron. And if we look at the successive ionization energies, we can tell that this in fact has 1 valence electron. Doesn't take a lot of energy to remove that 2s1 electron. However, in order to remove the second, look how much the energy jumps up. And that's because as I get to this second electron, I'm removing a core electron. So remember, it takes us a lot more energy to remove those core electrons than it does your valence electrons. And that's why visible light or ultraviolet light can only remove valence electrons. It doesn't take a lot of energy to do that. So core electrons require a lot more energy to remove because of Coulomb's law. The closer those electrons are to the nucleus, that distance is much smaller, so therefore the nucleus has a much stronger attraction to those electrons, and therefore it holds on to them more strongly. And X-rays actually have enough energy to remove any electron from an atom. So if you think about the electromagnetic spectrum, if you've had me, radio waves, microwaves, infrared radiation, there's visible light, ultraviolet, what comes next? X-rays, and then gamma rays, of course. So if we want to study the whole structure of every electron in an element or atom, we can bombard it with X-rays and remove every single electron and then study the electron configuration that way. So let's talk about photoelectron spectroscopy. What is it? Involving everything we've just talked about. So this is an experimental technique that's used to determine the relative energies of electrons in atoms or molecules. So because with ionization energies, we've been talking about energies before, the higher the ionization energy means the more difficult it is to remove that electron. We can measure that. We can measure how much energy it takes to remove different electrons depending on where they are around that nucleus. So if an atom is hit with enough energy, any of its electrons can be ejected. That's what X-rays do specifically. So photoelectron spectroscopy identifies the binding energy, or in other words, the ionization energy for all electrons in an atom. So we are able to determine how much energy does it take to remove every electron from an element. Let's go ahead and talk about how this works. So here is an atom of anything, and scientists will bombard this with X-rays. And when they bombard it with X-rays, of course, it's going to strike the sample, and then electrons are going to be emitted from that. So when a photon, which is a fancy word for a particle of radiation, when this particle of radiation strikes an electron, that electron leaves the atom. So it's ejected from that. That is what we call a photoelectron. So these X-rays have to hit the electrons, and when they do, it forces the electrons to leave. And electrons with a very low binding energy exit with a high kinetic energy. Those electrons that are not very tightly bound to the nucleus leave at a much faster velocity. They leave at a much with more kinetic energy than those electrons that are more tightly bound. That makes sense. If it's very easy to remove something, it's not going to take a lot of energy to move it. Whereas electrons that are very close to the nucleus and are very tightly bound, it takes a lot more energy to do that. So they leave with a much lower kinetic energy. And of course, scientists can measure that kinetic energy. So this is what an example spectrum would look like. So in this case, you have your binding energy on the bottom. And binding energy is another way of saying how much energy does it take to remove an electron. So it's kind of similar to ionization energy in that way. And then on your y-axis, you have the intensity of that. And the intensity, the higher the intensity means the more of those electrons there are. So rather than say intensity, chemists usually use the relative number of electrons. So what that means is that the higher the peak, the more electrons exist in that particular energy level. And you'll notice that these are actually to me, they seem backwards because the higher binding energy is actually towards the left. So these electrons here would be more tightly bound to the nucleus. It takes more energy to remove these electrons than it does the one over to the right. So kind of backwards to me, but if you are aware of your axis on the bottom, the binding energy is 100 on the left and it's 0 on the right, you should be able to determine it. So let's go ahead and look at how this actually happens. And we are going to analyze a sample of lithium. So you'll see here that we have 3 protons in the nucleus, some number of neutrons, it doesn't matter. And then I have 3 electrons in my energy shell surrounding that. So here's my energy source. So here's my X-ray source. I have this kinetic energy analyzer. And up here on the right-hand side, we're going to start creating a spectrum from this. So what'll happen in a photoelectron spectroscopy instrument is we're going to bombard these lithium atoms with X-rays. So look how these X-rays come in. They're going to hit those electrons. Those electrons become ejected from that surface, and then they go into the kinetic energy analyzer, and that amount of energy is measured. And you'll see that as this continues occurring, your spectrum is going to start looking a little bit different. So notice how electrons are constantly moving. So I have some jumping up from lower lithium atoms that are down there towards the bottom. They're jumping up to other shells. Some electrons actually aren't making it into the analyzer, but some of them are. That one just did, so that peak is still growing because the intensity is much greater there. And you might end up with a spectrum that looks a little something like this. So this animation is now finished. This is what your output from that instrument would be. So what does this mean? So that photoelectron spectrum would actually look something like this, and that is the spectrum for lithium. And you'll notice that there are 2 peaks that would come from that particular experiment. So there's 2 peaks right here, and that means that there are 2 different types of electrons that exist in lithium. So there's this peak here and this taller peak, and then I have this much smaller peak over here. And notice that the peak sizes are very different. And in fact, if you were to measure this peak here on the left is twice as tall as the one here on the right. So therefore, because this measures the intensity or the number of electrons, because this peak is twice as tall as this one here on the right, that means that there are twice as many electrons that live in this particular subshell. And that's something to keep in mind as you look at photoelectron spectra. So the height of the peak represents approximately how many electrons exist there. So here's another one. Let's look at boron in this case. So we're going to determine the photoelectron spectrum for boron. So I'm going to start my X-ray source here, and notice those electrons are getting ejected. And you have some electrons moving around. That electron didn't make it into the analyzer, but your electrons continue to hit that. And you're going to continue seeing this peak emerge, or these peaks. So right now I have about 2 peaks. Looks like they're about the same height. Oh, I have a 3rd peak that just came from that. And this is going to keep occurring until eventually your instrument is done reading the results. So we'll just let this run here for a little bit and see what happens. Continue getting our spectrum here. Still analyzing. So that those X-rays are still hitting these electrons here. And it looks like we're done. So there's our spectrum for boron. Let's compare that to lithium. So it looks like boron, holy moly. Holy moly with boron, look at these electrons here, has a much higher binding energy. These electrons were significantly harder to remove than these other sets of electrons down here. Whereas lithium, if you were to compare, it looks like it's on the same scale here. Much, much different, the photoelectron spectrum for lithium. So let's go ahead and analyze. What does that mean, boron's photoelectron spectrum? So this does in fact have 3 peaks. So if we consider the electron configuration for boron, it would be 1s2, 2s2, 2p1. So we can correspond each of those elements of that electron configuration to this photoelectron spectrum. How many electrons are represented by each peak? Let's answer that question first. Well, this one right here, if this is its electron configuration, boron's electron configuration, this first one has to represent 2 electrons. And you're going to see that the first peak on every photoelectron spectrum is those 2 electrons. Therefore, because this second peak is the same height, this must also represent 2 electrons. Whereas this third peak here represents your last electron, which is that 1 valence electron. So I'll say 1 electron. And that's because this peak is half the height of that one. So there's your 5 electrons total. 1, 2, 3, 4, 5. And which peak represents the electrons closest to the nucleus? Remember, Coulomb's law, electrons closest to the nucleus are the hardest to remove. Therefore, they have the largest binding energy. It takes the most energy to remove those. Remember, it's backwards on a photoelectron spectrum. Right here, looks like I'm at about, I don't know, maybe 30 megajoules per mole. These are the most tightly bond right here. So these electrons are the closest to the nucleus. Closest to nucleus. It takes a lot of energy to remove those. They're in that first shell. As opposed to the furthest, well, your electrons that have the lowest binding energy would have to correspond to those. So this 1 electron is the furthest away. And that makes sense because you have 1 electron in that p subshell, and that p subshell exists a little bit farther out than the s subshell. So of course these ones would be the ones in the center, your 2s2 electrons there. So just remember, you do have to look at the scale at the bottom. So in this case, over towards the left-hand side, these are always going to be closest to the nucleus. It takes the most energy to remove those electrons. They have a very high binding energy. Whereas these ones over here towards the right have the lowest energy. They're going to be your valence electrons, the farthest from the nucleus. Very easy to remove because of that great distance between them. So here is a comparison of hydrogen versus helium. 2 photoelectron spectrums kind of just put on top of each other. And you'll see here, one is a dotted line and the other one is a solid line. So question, which one is helium and which one is hydrogen? Well, you can tell very easily just by looking at the height of each of these peaks. So helium would be this guy right here. Helium has 2 electrons in its outermost shell, or total rather, whereas hydrogen has only 1 electron. So this first peak, the one over towards the right here, must correspond to hydrogen, whereas this peak must correspond to helium. And really, I only know that based on the height of each of those. Why does one have a higher binding energy? So we're talking about helium. Why does helium have a higher binding energy? Its electrons have a higher binding energy. Why does it take more energy to remove those 2 electrons? Well, we could say this for a couple of reasons. And of course, the first reason I'm going to have you explain deals with Coulomb's law. So because these 2 electrons, because the nucleus has a more positive charge, and that distance will start to decrease from the outermost shell to that nucleus. And because those electrons are therefore more attracted to the nucleus, they are more difficult to remove. So your binding energy is greater. So we'll say binding energy for helium is greater, and this is because the electrons are more tightly attracted, or strongly attracted rather, I'll just keep tightly there for now, to the nucleus. And this is really what it comes down to. Photoelectron spectra really doesn't get any more complicated than this. We're going to work through a couple of examples here together just to kind of get you familiar with elements that are a little bit larger than the first 4 on the periodic table. So here is a photoelectron spectrum for beryllium. So notice that the peaks are the same height, which means that they both have the same number of electrons. This one here, of course, your first peak, the one furthest to the left, will always have your 2 electrons. So this means that this guy also has 2 electrons, and you could tell just based on the height of those. Let's see here, 2 peaks of equal height. Therefore, there are 4 electrons in beryllium. Each one has 2 electrons each. Notice that the binding energy for your core electrons is much higher. It takes a lot more energy to remove those, which is why you have a peak so far to the left. These ones here are going to be your valence electrons. Those are the 2 in that outermost shell. Let's take a look at another one here. So this is for carbon. So carbon has 6 total electrons, and here's its structure up here. It's got 6 protons in the nucleus. Each of these peaks are of equal height, which means that they all have an equal number of electrons. So each of these corresponds to 2 total electrons, 3 peaks of equal height, 2 electrons each. Look at where these peaks are located as well. So these are going to be your 1s2 electrons, very high binding energy, almost 50 megajoules per mole. Takes so much energy to remove those innermost electrons, those core electrons, these 2 right here. Again, because of Coulomb's law, that there's a much smaller distance between them. This second peak right here, these would have to be your 2s2 electrons. And then we have our 2p2 electrons, which are going to be the easiest to remove. Here we are for nitrogen. So we're starting to get a much larger final peak here. So I still have 2 electrons here. Those are my 1s electrons. I have 2 electrons here. So notice that each 2 of these looks like it represents 1 electron. So this right here is 1 electron. And then this distance right here is 1 electron. 1 electron. So it looks like onto this next peak here, I'm adding 1 additional electron. So the total in this case is going to be 3. Those are your 3 2p electrons that are coming from that. So I have 3 peaks of different heights. The first 2 are the same. I do have an additional electron on that last peak there. Like I said, which means that there is only 1 more. Here's oxygen. So oxygen has 6 electrons in total, 2 electrons here, 2 here. It looks like this peak is double the height. So here it is, 1, 2, 3, 4 going up. I have an additional 1, 2, 3, 4 on top of that. So this final peak represents our 4 electrons. So for oxygen, like I said, we do have 3 peaks. And that last peak there has twice as many electrons, which contributes to its overall electron configuration. So this would be 1s2, 2s2, and then 2p4, which makes sense based on that spectrum there. Neon. So let's look at this one here. So neon has 10 protons in the nucleus, 10 electrons in the 2 energy shells around it. So how many electrons are represented by each peak? So this first one, oh my gosh, look at that binding energy. It is so high. It takes so much energy to remove those 1s electrons. So this right here, this first peak is always 2. And that kind of gives us a scale on how to read each of these. You're not always going to see photoelectron spectra that look this good, especially if you're doing it for real, like on an instrument. They're not going to be this perfect. So if each one of these lines is 1 electron, so this is 1, this is 2, that means this last peak must represent 1, 2, 3, 4, 5, and then 6 electrons there. And then the next question is asking which peaks represent the valence shell. The valence shell is your outermost electrons. And remember, there could be more than one. So if I consider neon's electron configuration, 1s2, 2s2, 2p6, we actually have two peaks that should represent the valence shell. So your answer is both of these right here. And notice how much less energy it takes to remove those electrons relative to this one that's super close to 100. So your valence shell, they're going to be the easiest to remove by far. And we can really just keep going. So how many electrons are represented by each peak? First one here is 2. Notice how now this first peak actually is even more difficult to remove because we added a whole shell around the nucleus here. So this one would be your 2 electrons. Looks like I have another 2 because that's the same height. Looks like this one would be 6 electrons. And then I have 1 electron right here. So how many electrons are represented by each peak? That's done. Sodium forms a cation with a positive 1 charge. And the question is why? And the reason why is because this binding energy is so little. It doesn't take a lot of energy to remove that electron. Sodium is practically giving it to anything that's willing to take that electron. That's why sodium is so reactive. So because this binding energy is so low, it's going to lose an electron very easily. The next one is asking, predicts the photoelectron spectrum of magnesium. So what I'm going to do is I'm going to try to make a scale here. So I'm going to go from try and make it the same as this right here. So I'm going to make this guy all the way here to be 1,000. And I'm going to make this side here 0. And it's not going to be to scale because I'm not going to be the best at this, but let's go back here and just double check. Yeah, this is not to scale either. So these guys are like way far out to the other side. So I'm just going to do 100. That's not to scale either. Nope, that's not to scale at all. Let's try that one again. So I'm going to draw 10 in the middle. I'm going to draw 1 right here. And I'm going to draw 100 right here. So magnesium, as we know, is a little bit smaller than sodium. So let's consider its electron configuration. We have 1s2, 2s2, 2p6, and then 3s2. These 1s2 electrons, let's start off there. Are these going to be harder to remove than sodium's, or are they going to be easier to remove? They should be harder to remove, and that's because as you add that additional proton to the nucleus, look, I have 11 protons in the nucleus, and now I have 12. That means that this first peak should be a little bit more towards the left. So I'm just going to draw a peak right there. Not a very good one, but you get the idea. So there's my first peak. That's my 1s2. Then I have my 2s2. So I'm going to draw that one somewhere in between the 100 and the 10. I'm going to just compare that here to the one before it. And I'm going to draw that next set a little bit closer to the 10 in this case, only because that nucleus is a little bit stronger. So I'm going to draw my next peak right about here. There's my 2s2. And then I'm going to draw my 2p6. This one should be relatively close to the one before it. Let's just take a peek here and see. Yeah, I'm just going to draw this one kind of right next door. You're not going to be asked to do like a totally perfect photoelectron spectrum, but wonderful, there it is. And now, does it take more or less energy to remove those 3 s electrons, the 2 of them from magnesium, than the 1 from sodium? You should say that it should be more difficult to remove because of that increasing nuclear charge. So right here, we're a little bit closer to the 1, probably at about 0.7, I would say. We have to take this peak and move it a little bit more to the left because they're a little bit harder to remove. Not only move it a little bit more to the left, but we have to actually double that one. So I'm going to take this guy and move it just a little bit right there. And I'm going to make that the same height as these first 2 right here. And that would be a very nice representation of a photoelectron spectrum for magnesium. So how many peaks would you expect? There are 4. So this would be 1 peak, 2 peaks, 3 peaks, 4 peaks. And there would be two electrons represented by the first, second, and the fourth. And that's because they're all the same height. Whereas this third one here represents 6 because it is 3 times taller than the other 3. And if we look at what it actually is, you'll see we did a pretty darn good job of identifying what it would be, even based on where they're located. So there it is. There's the real one. And what ion would magnesium form? So because this energy is very low right here, magnesium would form an ion with a +2 charge. And that's because it's relatively easy to remove those valence shell electrons right here. Sorry, I'm not going to rewrite that. It's just, you know what I'm trying to circle. I have this pad here and it's not that large, so sometimes I can't write on there well enough. So those are your valence electrons right there, very easy to remove. So why do we do this, right? What the heck do we care about photoelectron spectroscopy? Well, it actually adds quite a bit about this whole model theory of the atom. We don't know that an atom is for sure what it looks like with the shells and everything because we can't see them with our own eyes. But using this type of instrument and bombarding these electrons and bombarding these atoms with X-rays, and we're able to quantify those energy values, we are able to further prove that our current model of the atom is in fact real, that it does work. So along with that, all electrons within a shell do not necessarily require the same amount of energy to remove, which is important, not just in what we're talking about in this class, but when you talk about quantum chemistry, you're going to do lots of crazy calculations with electrons and energy shells. And each of those electrons, depending on where they're located, takes a different amount of energy to remove them, like our successive ionization energies that we were seeing in the first part of this unit so far. And within each shell, there are distinct groups of electrons that have distinct binding energies. So that's like our 1s, or 2s, or 2p. We're going to see that they are very different. So for example, we have our group of 2 electrons, so that's like our S subshells, right, which is what it says down there. You have S subshells, and you also have those P subshells. It takes a different amount of energy to remove electrons from each of those. And I have this thing right here. I'm not sure why I put this in here, but these are what your S clouds look like, and then your P clouds look a little something like this. I'm not going to focus on this. This is not something you're assessed on your AP chemistry exam, so I am not going to worry you with shapes of orbitals. But there's a lot of chemistry that goes into that. Let's talk about the shells in argon. So argon has 18 total electrons. So if we look, we can clearly see those 3 shells. And I popped that first one up there for you. So in red, this first peak right here are those first 2 electrons in argon, 1s2. There they are, closest to the nucleus. Holy moly, about 500 megajoules per mole to remove those electrons. Right here, we have our second shell. The one in the center requires intermediate amount of energy to remove those. Whereas our third energy shell, that outermost one, requires the least amount of energy. Notice how we're actually not substantially, but quite a bit before 1 than we were with some of those previous elements we were talking about. So although it looks like these are relatively easy to remove, jumping from about here to about here in chemistry is a big jump. So really, we're not going to be able to remove those electrons very successfully at all for argon. So furthermore, we can identify not only what shells, but what electrons they are specifically, whether you're S or P, based on their height. So like I told you, the first peak you're going to see on a photoelectron spectrum is always going to be 2 electrons. So you always know the height of 2 in this case. So that's why this guy here is 2. Here's your 2s, which also has 2 electrons, and your 3s, which also has 2. in this case, notice your P, because argon has a full outer shell, 6 electrons in the P sublevel each. They're also the same height. So it makes sense if you look at the spectra and then you consider the electron configuration, you're like, oh my God, like this is how we get this information, and this is why we do all of the things that we do. This is why argon doesn't lose or gain electrons, but sodium does lose an electron and fluorine gains an electron. So this photoelectron spectroscopy is a whole method of helping us to study elements even more than we already do. So starts with the highest binding energy subshell and with the lowest binding energy. We've talked about that. And then the superscript is the number of electrons in that energy shell, which is what we've been talking about all along. 2 more. So right here, a lot of times you're going to be given a photoelectron spectrum and you're going to be asked to identify the element. You're not going to have to do this for any elements like literally beyond argon. So if you can do up to argon, like that one we just talked about, you can do any photoelectron spectrum I'm going to give you. So we do know that this first peak here has 2 electrons because that is always true. Because this second peak is the same height, this one also has 2 electrons. And then if I count here, it looks like every one of these is 1 electron. So 1, 2, 3, 4, 5, 3, 4, 5. Looks like this corresponds to 5 electrons. So 2 plus 2 is 4, plus another 5 gives me 9. 9 electrons total. Looks like this would be the photoelectron spectrum for fluorine. Fluorine. So if you consider your electron configuration for fluorine, it would be 1s2. And then we have 2s2. And then finally we end on 2p5. It all comes together. This is also asking for the orbital diagram. So let's go ahead and draw that orbital diagram. Orbital diagram deals with the lines like this. So we have our 1s subshell, our 2s, and right here is our 2p. And then we would draw our arrows. So 1s2, 2s2, and 2p5. Remember, follow Hund's rule first, because electrons don't like to be on the same line because they repel each other. Coulomb's law, they have the same charge, they don't want to be next to each other. Then we'll face them down. There is our orbital notation for this element. One more, bringing it all into the circle. So this guy right here has to represent our 2 electrons, right? Even though this peak is much higher than this one here, it doesn't matter. That peak all the way to the left will always be your 2 electrons. This peak right here, half the size, this must be 1 electron. So 2 electrons plus 1 electron, guess what? Is the element lithium. We came full circle here. We first started talking about lithium, and now we're going to end on lithium. So let's draw the orbital notation. It's got 3 electrons, so I have my 1s and my 2s, and I have 1, 2, and then 3, like that. That is photoelectron spectroscopy. It does not get any more difficult than that, which is why I was comfortable giving this to you as an at-home assignment to watch and take notes on, and you're going to do a worksheet that corresponds with this as well. If you have any questions, please make sure you ask me in class the next time I see you. Otherwise, I will see you in person soon in the next video, and I hope you have a great day. Bye.